All right, this is sixth grade, Unit 1, Lesson 4. And in this lesson, students are going to be taking what they know and remember about the area of rectangles, and they're going to apply that to the area of parallelograms. And first, we're going to have to kind of refresh our memory about what the heck a parallelogram is. So let's get started. So we're going to begin with a warm-up and where students are just supposed to ask, what the heck is a parallelogram? And then we're supposed to refresh our memory. Now it says figures A, B, and C are parallelograms. And then it says right here, and then it says that figures D, E, and F are not parallelograms right here. So we're supposed to figure out, okay, so what are all the basic things? What do we notice about the examples and non-examples if everything above the green line are parallelograms and everything below the green line are not parallelograms? So let's talk about what is the number of sides that a parallelogram has. So we can see that it looks like, whoa, I want this one red, that parallelograms all have 4 sides. 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Man, my pen's having issues right here. And so we see that parallelograms have 4 sides. How many are opposite sides of the parallelogram? What about the opposite sides? What do we notice? Well, opposite sides seem to be parallel. Opposite sides seem to be parallel. Opposite sides seem to be parallel. Not only are opposite sides parallel, but it appears as though the opposite sides are equal to each other, the same length as each other. The opposite sides seem to be the same length. All right, so that's what we're noticing about parallelograms. And we notice down here, oh, and lastly, let's take a look at the opposite angles. We see that this is an obtuse angle, that's an obtuse angle. And we see that this is an acute angle and this is an acute angle. So it kind of looks like they seem to be equal. So it appears as though opposite angles, this is an opposite angle, these opposite pair of angles, and this angle are opposite. And it appears as though the opposite angles appear to be equal. And then when we look at these non-parallelograms down here, below, we see that, here we go, that while this has 4 sides and this does not have 4 sides, so that's automatically not a parallelogram. But we can then say, well, what about the opposite sides of the parallelogram? And we see that these opposite sides are not equal. These opposite sides appear to be equal, but remember, there's not 4 sides. They have too many sides. So that's kind of excludes it from the parallelogram. And here, these opposite sides are parallel, but the opposite sides are not equal. And so that's why these above the green line are parallelograms and these below the green line are not parallelograms. So in this section, this is the main activity, parents and teachers. And so in this main activity, we actually have 2 main activities today. We're going to find the area of each parallelogram. We're going to allow our students just time to think and grapple and struggle. And we're going to start with this first one. And students are likely, there's a variety of ways that we're going to want our students to, grapple with finding the area of this parallelogram. One thing they might do is they might just start individually counting every single square. 1, 2, 3, 4, 5. And initially they might skip all those fractional squares and they might just count all of these squares, 9, 10, 11, 12, etc. And then they're going to start piecing these together, like these 2 together equals 1. They might piece these 2 together equaling 1 and these 2 together to equaling 1. And so they might count that way. That's one way that students might attack this problem. That way it would work on this problem. It's a fairly simple and appropriate approach on this with this particular parallelogram. But another idea that students might do is they might take this entire triangle. They might recognize that, oh, I see a triangle right here. And they might take that triangle and they might rearrange it, because that's what we've been doing before, is recognizing that you could take a shape and rearrange it, decompose it, rearrange it, and you still have that same area. You might have a different shape, but you'll have the same area. So we can see that by taking this thing and moving it over here, so we still have this right here. So there you go. There's our triangle that we removed, and then all this stuff got removed. In fact, maybe I should do it in white, huh? So all this gets moved away, and then we have a really nice, easy rectangle that we can recognize, and we can see that it's, well, let's do it in green. We can see that it's 1, 2, 3, 4, 5, 6. It's 6 tall and 1, 2, 3, 4, 5, 6 wide. And there's and that's easy to find the area. That's 6 times 6 is 36. So that's another way. It's that that idea of recognizing that we can take this triangle, move it over here, and now we have the shape of a square right here, and that's how we're going to do it. There's another way that students might attack this problem. They might think of the entire enclosing figure, and I'll do it, let's say I'll do it in green. They might look at this entire enclosing figure right here and say, okay, that entire enclosing figure appears to be a rectangle, because it is. And we know that this rectangle is 6 tall, and I don't know what it is wide, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 units wide. So we can see that 6 times 9 is 54 units squared, right? So we know that that entire figure has an area of 54. But then what we can do is we can say, well, but we have this triangle here, and that triangle, and this triangle here, and we can take those two triangles. Now, let's see, how am I going to do that? I could take that triangle and this triangle and piece them together, and that creates a rectangle. And that rectangle, we can see, has a height of 6 and a width of 3. So this rectangle right here, that combined rectangle, has a height of 6 and a width of 3, which means that rectangle has an area of 18. Oopsies. That rectangle has an area of 18. And so we need to subtract 18 from the area of 54. We need to do 54 subtract 18, and that's how we're going to get our answer. And what is that, 36? It looks like it's 36. And so we can see, because the area of the entire rectangle is 54, but subtract out, but subtract out the fact that this triangle plus this triangle equals a rectangle of 18. So 54 minus 18 is 36. So we have a variety of ways that students might approach finding the area of this parallelogram. So parents and teachers, we want our students to explore, and I only showed some of them. I didn't show all of them. There's other ways that students might approach finding the area of this parallelogram. And here's another example where students can attack this problem. Here I can see that if I were to find this triangle right here, and if I were to slide that triangle over here, so now this piece would be gone because I rearranged it. I moved it over to here. I now have, let's see, I want to do it in purple. I now have a new rectangle 3 units tall, and let's see, 1, 2, 3, 4, 5, 6 units wide. So 3 units tall, 6 units wide, so 3 by 6 gives us 18 square units. There's other ways we can solve it, but I'm going to just leave it right there. And so parents and teachers, this whole part, this this part right here, that's about 15 minutes worth of exploration, discovery, and then sharing and comparing ideas. So as we move down to the next part, this part's another 15 minutes or so, and this gets tricky because the idea is we're going to be causing students to explore new ideas for how they're going to find the area of this parallel of each of these parallelograms. So they design these parallelograms to force students to use new strategies. On parallelogram A, I think most common, students are going to decompose this triangle and they're going to slide it up to create a brand new rectangle, 3 units wide, 1, 2, 3, 4, 5 units tall, because this piece is going to go away because it gets moved up to there. And so now 3 times 5 gives us the area, which is 15 units squared, right? And really, I should do that in a different color. So let's call that 15, there you go, 15 units squared. So that's a common way. B is wonderful. This is kind of really sneaky and tricky. You know, a common, I don't know if it's common, but a way, I think the way I would approach it, maybe, is I see that if I were to take a look at this triangle right here, the part that is not part of the parallelogram, and then I'm going to look at the same kind of triangle here on the opposite side. There we go. Okay, so basically what I've created is I've created a big, huge rectangle right here, a big enclosing rectangle. And I can see that that big enclosing rectangle has, let's see, has a height of 1, 2, 3, 4, 5, 6, has a height of 6, and it has a width of 1, 2, 3, 4, 5, 6, 7, 8, 9, has a width of 9 units, so that I can see that the big enclosing rectangle has an area of 54 units. Okay, but now what I can do is I can, let's see, let's get rid of that big enclosing rectangle right here. And then I can notice that these triangles that I had originally drawn, I can kind of squeeze them in. Look at that. See, I can just slide it over and I make a new kind of rectangle that isn't actually part, this is the part that is not part of that huge enclosing rectangle that is not blue, right? So I can take that, I can scooch it over here, and I can see that it has a height of 1, 2, 3, 4, 5, 6, and a width of 1, 2, 3, 4, 5, 6, 7. I can see that it has a width of 7. So I can see that that forms a rectangle that is 6 units high, and it has the rectangle has a width of 7, so 6 times 7 gives us 42. So this white piece right here, the white or non part, and this piece right here, total equals 42 units. So 54 minus, which is the entire thing, minus the 42, which is this plus this. 54 minus 42, what the heck is that? That's 12. That's 12 units squared. And so what is that 12 units squared? That's the blue part right here that's remaining. So that's one way to do it. There's other ways to do it. And here we go. We've got another figure right here. I think the most common way that we might approach this, and is the classic way, is going to be to take this piece, this little triangle, rearrange it over to here. So the original base was 6, but then when we move it over, the base remains 6. So that base is still 6. It just got kind of shuffled to the right a little bit. And so now we have a nice rectangle. That rectangle has a height of 4 units. It's right here. The base, the width of that rectangle is still 6 because all we did was slide it to the right. So 4 times 6 is 24 units squared. So there's our common way of getting that area. And so the lesson summary is, okay, so what is a parallelogram? A parallelogram has 4 sides. The opposite sides are parallel. That the opposite sides are of equal length. And we also learned that the opposite angles are of equal length. And so that's the big takeaway of what a parallelogram is. We also learned that parallelograms can be rearranged to make rectangles, and that rectangles are easy to find the area of. So now let's take a look at the homework. All right, so for this first problem, it says to select all of the parallelograms, and for each figure that's not a parallelogram, explain how you know it's not a parallelogram. So we take a look at A. A is definitely not a parallelogram because while these two sides are parallel, these guys are not parallel. So there's our nice, so that is definitely no. Taking a look at B, we see that, well, the opposite sides are parallel. And we see that these opposite sides are parallel. We see that the opposite sides are also equal, or there. We also see that they're congruent. We see that the green side and green sides are equal to each other, and the red sides are the same length. So that is definitely a yes. All right, let's take a look at C. All right, now C, kind of tricky. You're going to say, well, it's not a parallelogram because it's a rectangle. Well, yes, indeed. But the opposite sides are parallel and equal. Here, the opposite sides are parallel and equal. And then we can even go so far as to say the opposite angles are equal. So this, while it looks like a rectangle, it is also a parallelogram. So we have a parallelogram. Yay! We see that this is not a parallelogram because we got some sides that are, well, first off, we kind of see 1, 2, 3, 4, and 5. So first off, it's not a parallelogram because it's got 5 sides. So we definitely know that is not a parallelogram. And we definitely know that E is not a parallelogram because it doesn't have 5 sides. So there we go. Only B and C are parallelograms. Question 2A and then 2B. So 2A says decompose and rearrange this parallelogram to make a rectangle. Okay, so they're kind of giving us the suggestion of which strategy to use. Then it says what is the area of this new parallelogram, the rectangle, which is the same area as the parallelogram, right? So all right, so let's do that, and I'll dig into this. And it says they want us to decompose the parallelogram to make it a rectangle. So I'm going to see that triangle. I'm going to move it over here. And when I take it and I move it over here, I get a rectangle. And I can see that new rectangle has a height of 5 units. And it has a width of 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So the area, 5 by 9, equals 45 square units. And we know that that's the same area. So the area of this new rectangle right here, the area of the new rectangle has the exact same area of the original parallelogram because all we did was slide the triangle from here over to here. All right, and so that's all we did. And so that takes care of 2A and 2B. Let's see, find the area of the parallelogram. Find the area of the parallelogram. Okay, so that's straightforward. We're going to do the exact same thing. So we know that the base, the width of the parallelogram is 10 because it says so, right? So if I take this little piece right here and I move move it over here, I know that the width or the base of this new resulting rectangle is still 10, because the new rectangle is right here. Here's the new rectangle right here. And oh, that's ugly. So let's do it in green. So the height is 3, the width is 10, and that's the new resulting rectangle. So it has a height of 3, it has a width of 10, so 3 times 10 gives us 30 units squared. So here's the thing. You might say to yourself, though, okay, so first off, the original parallelogram included the triangle way over here. I could kind of take this rectangle and temporarily move it for a second. So and actually I can move this over here as well. And you might be saying, well, wait, what happened to this 3.2? Why didn't we use this 3.2? Well, it's not necessary in this problem. It tells us the slant length, the length of this slanted thing, but that's not going to help us in this problem because we need to find the area of a rectangle, which has nothing to do with this slanted length right here. It has everything to do with the height, and the height is 3. So that height is 3. So that what matters is the 3, not the 3.2. And so that is how we got that area of that. Now, question 4 says, explain why this quadrilateral is not a parallelogram. So we got to look at this thing and say, well, why is it not a parallelogram? Well, we could see that the top and the bottom are parallel, but the key thing is they're not the same length. That the one on top is not the same length as the one on the bottom, so therefore we automatically know that it is not a quadrilateral. There's other reasons, but that's once you found one reason, you're done. All right. Question 5 is a review from lesson 3. Find the area. And so I'm going to look at this really cool shape, and I'm going to say, well, it looks like I can take this triangle right here, and I can slide it over here. So this guy is no longer there. And I can take this triangle right here, and I can slide him down here. So this shape, oops, I'll keep it in red. So that's no longer there. So what's the new shape that we're really looking at? The new shape that we're really looking at is this right here. This is the new shape that we're looking at. And if I wanted to count the area, I can literally count. It's quicker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So the area is 12 square units. Right here, ooh, this looks a little tricky, but it's kind of fun. It looks nice. So what we could do is we could say, I can see that I could take this triangle here, and I can rearrange it down here, but I'm going to have to rotate it, aren't I? So I'm going to have to rotate and flip. Whoa. I'm going to have to rotate and flip. So this piece right here is the same as this area down here, but I have to rotate and flip. So I can't do it with my little drawing thing. So this is gone, and then I can do kind of what looks like the same thing. It looks like if I take, let's see, well here, I could take this whole thing right here, and I can bring it around, and it creates this rectangle down here. So this shape is no longer here. So if I wanted to outline some portions in blue, I could see I've got a rectangle right here. It's 3 units by 5 units, so it's got an area of 15. I could see this new rectangle over here has dimensions of 1 unit by 4 units, so it's got a unit area of 4. So 15 plus 4 gives us our 19 units squared. And then our last question, question 6. Find the areas of the rectangles with the following side lengths. So basically, we know that the area is found by length times width. So if we're going to do 5 times 1/3, that gives us 5/3. And if we really wanted to, we could say 1 2/3 inches squared. How about B? B is length times width. So that gives us 20 thirds. And if we wanted to rename that, we could say that's 6 2/3 square inches. Number C, 5/2 times 4/3 gives us 20/6, which equals 10/3, which equals 3 1/3 inches squared. And of course, nobody measures inches as 4/3 inches. That's kind of a silly question, but whatever. Okay, and then the last one, length times width equals 42/42, which is definitely 1 square inch. And there we go. That wraps up. So that wraps up Grade 6, Unit 1, Lesson 4.